Okay, in in this video, we're going to continue to play around a bit with odd and even integers, but we want to look at a different proof technique, which is fundamental, will be used quite a bit in different proofs in this class, which is called proof by cases. Okay, it's still considered a direct proof technique, but we'll see that it's a little bit uh, different. And so now we want to prove something else. So now we say if n is any integer, then if you form this um, expression n squared plus n plus 6, you will always get an even integer. Okay, and we're proving this basically so we have an example of proof by cases, but in this class we're going to see many different examples of proof by cases. This is just our first very simple example so that we can start to understand this. And before I move on, I want to start explaining some of the logical structure here. So I'm going to rewrite this in a slightly different way. So I'm just going to say that n being an integer implies that n squared plus n plus 6 is an integer, but specifically even. Okay, and the reason why I want to do this is because I want to start pointing out to you the logical structure here. So here we can call this capital A. When I use capital A here, we're going to do a whole section on formal logic. And so A is going to stand for some statement. So in this case, the statement is that n is an integer. And then implies in logic is often denoted by this arrow, a double arrow like this. And then the conclusion I'm going to call also a statement, so I use a different letter, capital B. Okay, so we call this an implication statement, which many theorems in mathematics are of this form. And so we want to prove that A implies B. Okay. Again, we're going to do a whole chapter on formal logic eventually, but for now, I just want to start introducing these ideas. So many statements in mathematics can be put into this general structure of A implies B. Okay, let's just play a little bit around with some examples. So if I take an odd integer and square it plus itself plus 6, then what do I get? So I get 49 plus 7 plus 6. If you add those together, you get 62, which is even. And then we should just play around with what happens if I plug in an even number. So now I get 100 plus 10 plus 6, which of course is 116. Okay, so it's just interesting to note that if I plug in an odd integer, I get an even, and if I plug in an even integer, I get an even. So that's why the statement does make sense for any integer. Okay, good. Now, we're going to do this by proof by cases, and the reason is I just want you to first realize if you try to disprove this directly, you're supposed to take any integer, and then you're supposed to take n squared plus n plus 6. Okay, and now you want to show that n squared plus n plus 6 is even, right? If you want to show it's even, you're supposed to show that it's written as 2 times something else, right? So if we were trying to do that, we would say we want to show that it's like 2 times L. And let me put this in red because I don't know how to do that. So I feel a little handcuffed. Like I don't know how to make a 2 pop out of this expression. I mean, I know how to do it for 6. 6 can be written as 2 times 3, but I don't know how to make 2's appear in the n terms here, right? So I don't have anything to work with. But I noticed that if I knew that n was even, right? If n was equal to 2 times k, well, then I know what to do because I would just rewrite n squared plus n plus 6 as, well, 2k squared plus 2k plus 6. And then I know how to make this work, right? I pull a 2 out of everything. So if I pull a 2, I get 2k squared plus k plus 3. So if that was the case, then I know what to do. And similarly, if n was equal to 2k plus 1, if it was an odd integer, then I argue that we also know what to do, because I would take n squared plus n plus 6. I would rewrite it as follows. And then I would, you know, expand everything out and try to make it look like an even number, right? So if I expand this out, I get 2k squared plus 2k plus 2k plus 1 plus 2k plus 1 plus 6. Okay, I see these 2 plus 1s. I can add them all into the 6 at the end, and that will be even. And the rest I can rewrite as 2 times 2k squared. I can put all the 2k's together. That will give me 2 times 3k plus 2 times 4, because the rest gives me 8. And of course, now I can pull a 2 out. So then I get 2k, sorry, not cubed, squared. Let me erase that. 2k squared plus 3k plus 4. All right, so this was our proof sketch, if you like. I didn't call it a proof sketch because, well, in some sense you don't have to label your sketch. It's just you playing around, but I'll label it now. And now, though, I want to actually do the proof. But here, before we go write the formal proof, I just want to point out that we did a proof by cases where we say, okay, I don't know what to do in general. I don't know how to show you that n squared plus n plus 6 is equal to 2 times an integer in general. But I do know that if I assume it's even, I know what to do. And if I assume it's odd, I know what to do. And notice that's enough, because we said earlier there's a fact that every integer is either even or odd. So we've covered all the possible cases here. All right, so let's move on now and actually write out the formal proof, where I'll show you how to communicate a proof by cases. Okay, so now we start the proof, and I need to communicate carefully to the reader now. And so assume that n is an integer, and hence by fact 2, n is either even or odd. Now I'm pointing this out to the reader because I'm about to split into 2 different cases, and I want to bring it to their attention that those are the only 2 cases that I have to consider because of this fact. Okay, so now we will proceed to prove the proposition by considering both cases. Okay, so I'm just communicating to the reader that I'm about to prove this by cases. Okay, so case 1 is if n is even. Okay, so then in this case, n is equal to 2 times k or some k, right? So hence we can calculate n squared plus n plus 6, which is equal to 2k squared plus 2k plus 6. So notice, assuming it's even gives me something to work with. It gives me n is equal to 2 times k, and that gives me something to play with here. So now I can pull out a 2, and I'll get 2k squared plus k plus 3. And since, let's just point out to the reader the ending here, since 2k squared plus k plus 3 is an integer, by fact 1, we know n squared plus n plus 6 is even by definition 1. Okay, and in this last part, I've already been doing this several times, but I just want to point out that it's really important that when you make a claim in mathematics, oftentimes we want you to either revert back to a previous lemma, a previous proposition or theorem, or a previous definition. So that's what I'm doing here, just pointing out to the reader where I'm using different facts and definitions and theorems and things. Okay, so that's case 1. If n is even, then n squared plus n plus 6 is even. But that does not prove the proposition because that's not the only case, right? So now we have to go to case 2, which is the only other case, and that is if n is odd. Okay, so if n is odd, then n is equal to 2k plus 1 for some k. Hence, we can calculate. Okay, so now we have to do the calculation in the odd case. So we look at n squared plus n plus 6. We notice that the odd case is slightly more of a calculation, but that's okay. So now maybe we write out a little bit more here. So we get 2k squared plus 2k plus 2k plus 1 plus 2k plus 1 plus, maybe we write this as 2 times. Well, actually, we have to combine it with the 1, so maybe that's not helpful yet. Okay, so we can write this as 2 times k squared plus 2 times 3k plus 2 times 4. When I add the 1 plus the 1 plus the 6, that gives me 8, which I can write as 2 times 4. And now I have the 2 that I can pull out of all 3 terms. So we're happy. And now we just point out to the reader that since 2k squared plus 3k plus 4 is an integer by fact 1, we know n squared plus n plus 6 is even by definition 1. Okay, so those are the only 2 cases that we need to consider. And so now we just want to make a concluding sentence. So hence, n squared plus n plus 6 is even for any integer n. Okay, good. So this is a very useful strategy, proof by cases, because again, in this case, it wasn't clear how to show that n squared plus n plus 6 is even to begin with. But as soon as we knew that n was even or n was odd, we knew what to do in the proof. So it was helpful to consider cases here. In this proof, there was only 2 cases, but in general, you can have any number of cases depending on the proof. So there could be 3 or 4 or 5 cases. It really depends on the proof, and it depends on what you want to break things down into. So we will see this in many different examples throughout the rest of the class. This is just our first example of proof by cases.